In this video, we discuss using JK flip-flops to build a ripple counter and using D flip-flops to build a BCD binary coded decimal counter. We first discuss the ripple counter. As shown in this diagram, we tie the JKs of each flip-flop to high. That means the input values of JK are 1, 1. So the flip-flop toggles when there's a positive clock transition. In the circuit, the first flip-flop is driven by a clock, but the second flip-flop clock is connected to a Q0 bar of the first flip-flop. So when there's a transition of Q0 bar from 0 to 1, then Q1 changes state. And in the third flip-flop, the clock is connected to a Q1 bar. So when Q1 bar changes from 0 to 1, then Q2 toggles. Now note that when Q1 bar changes from 0 to 1, Q1 actually changes from 1 to 0. So the timing diagram here shows the detail. First, all the flip-flop values are 0, and when there's a clock transition, positive clock transition, this triggers Q0 to toggle from 0 to 1. Okay. But there's no change in Q1 value because when Q0 changes from 0 to 1, Q0 bar changes from 1 to 0, and there's no no stage change when there's a negative clock transition. Okay. On the other hand, in the second positive clock transition, Q0 toggles again. So it changes from 1 to 0. That means Q0 bar changes from 0 to 1. So it toggles Q1. So it changes from 0 to 1. Similarly, when Q1 changes from 1 to 0, or Q1 bar changes from 0 to 1, then it triggers Q2 to toggle from 0 to 1. Okay. So we have this timing diagram. As you can see, at the beginning we have Q2, Q1, Q0 as 0, 0, 0, and then 0, 0, 1 representing the value 1, then 0, 1, 0 representing 2, and then 0, 1, 1, 1, 0, 0, 1, 0, 1, and so on. So you can see that this acts as a counter, counting from 0, 1, 2, 3, 4, 5, 6, 7, and back to 0. Now, let's discuss how we implement this circuit using Verilog program. Actually, I've written the program. So this is the implementation of D flip-flop with reset, as we discussed before, and we use positive edge. And this is the implementation of JK flip-flop. So we have the input clock and input reset, and input J, input K, and output register Q, and output Y, QB, which is the complement of Q or Q bar. We use wire here so that the value obtained from Q, okay, by using a sign, okay, like this. Okay, so QB is basically the complement of Q, and so the implementation is straightforward. We have always add the positive edge CK and positive edge RST. Okay. So if RST, and we have Q assigned 0. Otherwise, depending on JK, if JK equals 0, 0, then there's no change. So the next stage of Q is equal to the current state. And if JK equals 0, 1, then we have reset. That means the next stage of Q is 0. If it is 1, 0, then we have set. Right? That means the next stage of Q is 1. And if JK equals 1, 1, then we toggle. Right? That means Q next stage is equal to the complement of the current state. Q is assigned negation Q. So this is a JK, and we use JK flip-flops to construct a 4-bit ripple counter or binary counter. So we have input CK and input RST, the reset, and output 3 to 0 4 bits Q, and also QB, the complement of Q. So we just create 4 JK flip-flops. The first is A, CK, RST. The JK values are 1, 1, and we have Q0, Q0 bar. The second we call it B. As you can see from this diagram, the clock is Q0 bar. So that's what we have. QB0 is Q0 bar. And then we set again JK values are 1, 1. And output Q1, QB1. And this QB1 is the input to the clock of the next flip-flop. Because C, and again we have RST as input. The JK values are 1, 1, and the outputs are Q2 and QB2, and this QB2 will be the input to the clock of the next state. So this is the clock of flip-flop D, and again the other input is RST. JK values are 1, 1, and the outputs are Q3, QB3. So it is very simple. And can you say write a test bench to test this? So this is the test bench. So we have inputs register clock and register RST, and outputs via Q 4 bits, QB 4 bits. So we just create an instance of the ripple counter. Say CK goes to CK, RST goes to RST. So Q goes to Q, QB goes to QB, and then we display the clock, the time, and Q. So we start with CK, the clock to be 1, and we set to be 1, so that all the Q values are 0. And then we set RST to be 0, so the clock will start to function. And we run this for 220 units, and for every 10 units we toggle the clock. So we can compile this suppose I compile this minus O out counter. So no error. So we run this. So you can see that we have these outputs. So the time at the beginning, the reset is 1, so everything is 0, 0, 0, 0, 0. And then the clock changes from 1 to 0. There's a negative transition, so there's no change in the value. And here, with the transition from 0 to 1, then the Q0 toggles. So we have 0, 0, 1. And when the clock changes from 1 to 0, there's no change in the value. And when it changes from 0 to 1, so we have the Q0 changes from 1 to 0, and Q1 changes from 0 to 1. And then next we have 0, 0, 1, 1, 0, 1, 0, 0, and 0, 1, 0, 1, and so on. Now, we can also see the timing diagrams by running this code using ISE. I suppose we make a directory called ISE, and we run the ISE. So ISE starts, and we click OK for the tips, and we can first close any current project, and we create a new project. So we create the directory we just created. Suppose we call the project name counter, and next, finish. And we can add copy of source to this project. The source code we just had. So there's ff.v, the one that we just discussed. And we also need to add the other source, the test bench. And then we have to click simulation. So this is the code we just discussed. I think we copied the wrong one. Let's try again. this should be this. Okay, the test bench. Okay, now this is the one we want. Okay, we just discussed. Okay. And we click here, and we can double click here to check the syntax. So there's no error. We double click here to run it. Okay, and we can click here to see the timing diagram. Click here. Now you can see that this is the clock, this is the reset. Okay, so when it is 0, then the clock places normal row, and you can see that so this is the Q, this is Q bar. Okay. So we have Q0, Q1, Q2, Q3. Okay. This is the complement of the corresponding bits. So at the beginning is 000, and then we have 001, 0010, 0011. Okay. And you can see that it changes state when there's a positive clock transition. Like here, when the clock changes from 0 to 1, it changes from 000 to 001. Okay. And here, okay, it changes. This bit changes from 1 to 0, and this changes to 0 to 1, and so on. Okay. So this is the timing diagram for the ripple counter. Now next, we'll discuss the BCD counter. Now this is a block diagram showing a 4-bit BCD counter with reset. Okay. So basically we will use 4 D flip-flops, okay. And this is the reset, and all the D flip-flops are driven by the same clock. Okay. So we have 4 bits output. We can call them the Q0, Q1, Q2, Q3. Okay. And this is the state diagram. So we start from 000, 0, then the next stage is 0001, okay. The next is 0010, and so on. Okay. So it counts all the way up to 9, okay, represented by 1001. Then it goes back to 0, okay, and so on. So this is binary coded decimal counter, because it only counts up to 9, represented by 1001. 1001. Okay. So we'll use 4 D flip-flops to implement this. Okay. And this is the state table. So this is the present state, represented by Q0, Q1, Q2, Q3. And the next state is Qt plus 1. We discussed before that Qt plus 1 is equal to dt. Okay. So that means they can be represented by d3, d2, d1, d0. So if the current state is 0000, the next state is 0001, as shown in this state diagram. Okay. And if the present state is 0001, the next state is 0010, and so on. Okay. So we have all the way up to 1001, okay. And the next state will be 0 again. Okay. And for other values of Q, we don't care, so that's represented by X. Okay. Now to construct this circuit, we have to find out the relation between the D's and the Q's. So each of these D is a function of Q3, Q2, Q1, Q0. For example, for D2, okay, we have to look at this column. Okay, so D2 equals 0 when Q3, Q2, Q1, Q0 is 0, 0, 0, 0, and it is 0 when it is 0, 0, 0, 1. So these values can be represented by a K-map as shown here. Okay. So we use gray code here. So here we have 0, 0, 0, 1. Okay, so we have 0, 0, 0, 1. Okay. And then 1, 1, 1, 0. So the 1, 1, 1, 0. Okay. Now remember, this is gray code. Okay. And then 0, 0, 0, 0. So others don't care. And we can find the equation for D2 by grouping the ones together. So for these two ones, we form this bubble. Okay. So we have from here to here, Q3 changes. So we get rid of Q3, so we have Q2 only. And from here to here, Q0 changes. So we get rid of Q0, we have Q1 bar. Okay. So we have this term Q2, Q1 bar. And then for this bubble, we have Q2 and Q0 bar. Okay. And then for the other term, for this guy, we have Q2 bar, okay, and Q1, Q0. Okay, so we have these three terms, and we can simplify this a little bit. For these two terms, we can take the Q2 out, and for this, we can group the Q1, Q0 together. So we have this Q2 and Q1 bar or Q0 bar. And then we apply De Morgan's rule to this term, so we get Q1 and Q0 bar. And this is still Q2, and this is Q2 bar and Q1, Q0. So we can see that if we consider this as a term, say A, so we have Q2 A bar or Q2 bar A. So basically this is an exclusive OR. So we have Q2 exclusive OR Q1 Q0. Okay. So that's how we obtain these D2 equations. Similarly, we can obtain the equation for D3 and D1 and D0. Okay. So these are the actual equations. So actually D0 equals Q0 bar, D1 equals D3 bar, and Q1 exclusive or Q0. D2 is equal Q2 exclusive or Q1 and Q0 as we discussed here. Yeah. And D3 equals Q3 Q0 bar or Q2 and Q1 and Q0. And now the implementation of this using Verilog is straightforward. So I have written the code. So this is the BCD counter. So we have the input CK, the clock, input RST, the reset, and 3 bits output. 4 bits output Q. And we just follow this Boolean equations. We define 4-bit D. So we basically assign D0 to be the complement of Q0 and D1 to be the complement of Q3 and Q1 exclusive or Q0 and so on. and we create 4 flip-flops. These are synchronously clocked, so all the flip-flops are driven by the same clock, same reset, and each of them has its own D0, D1, D2, D3, and its own D0 own output Q0, Q1, Q2, Q3, and the relation between D and Q is given by this equation, which is what we got. And we can easily write a test bench, which is shown here. So similar to what we had. So again, we have inputs, the clock, the RST, and outputs 4 bits Q, and we instantiate the unit under test. CK goes to CK, RST goes to RST, Q goes to Q, and then we output the 4 bits of Q and the clock. And again, at the beginning the clock is 1 and RST is 1, and we set RST to be 0, then the chips will work as normal, and we run that for 2060 units, and we toggle the clock every 10 time units. Now when we run this, we should have something like this. So let's first compile it. So you can see the output here. So again, it toggles when there's a clock transition from 0 to 1. So it counts as 0, 0, 0, and then 0, 0, 0, 1. Okay, 0, 0, 1, 0. Now when it goes from 1 to 0, there's no change in state. Okay. There's a change in state when there's a positive clock transition from 0 to 1. So you can see that it counts as a BCD counter, 0, 0, 1, 0, and then 1, 1, 1, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0, 0, 1, 1, 1, 1, 0, 0, and 1, 0, 0, 1, and then after that it goes back to 0, 0, 0, 0, okay, and then 0, 0, 1. So it works as expected. And again, we can run using ISE. So this is the test bench. So again, we double click here to check no error, and then double click here to run. Oh, sorry, some error. Let me try again. Oh, I think I need to update this DFF. Now you can see the timing diagram here again. So you can see that this is the clock, this is reset. So it counts as say at the beginning 0000, and when there's a clock transition, it becomes 0001, and the next 0010, and all the way to 1001, and then it goes back to 0000. Okay, so there's the BCD counter, and well, here's the text output, so you can try this yourself. Thank you, bye bye. Oh, maybe I moved this. Okay, maybe it was out of the screen, so you can see that it counts from 00000 all the way to 10001. And back to 0000. Okay. Thank you. Bye bye.